Hi all, Chris Weishaupt here, materials scientist with MAP Laboratories in Everett, Washington. A big part of what we do as materials scientists is help make the jobs of other engineers easier by providing insight, specialized testing, and optimization of various properties of the materials they're using. In this case, we'll be looking at an interesting use of X-ray fluorescence in which, instead of using the instrument for its typical application of measuring elemental composition, we instead used it to understand why some metal sheets were behaving differently when machining. Process engineers have been working with rolled tungsten sheets from two vendors. They noticed that it was difficult to get a consistent surface finish when machining these parts, and one vendor was especially bad when it came to gumming up their tooling. We decided to look at these tungsten sheets by three different methods. X-ray fluorescence, which would tell us the elemental composition and whether it matched the specifications. Vickers hardness, which is where you press a diamond and dinner into the sample and measure the resulting impression, which would tell us if there was a difference in hardness, and annealing history that could explain the machining differences, and microscopic examination of the metal microstructure. The focus here is primarily going to be on the X-ray fluorescence side of things. XRF uses an X-ray source to bombard a sample, ejecting electrons in the sample from their orbits. When other electrons in the specimen fall down to fill those vacant orbitals, they fluoresce characteristic X-rays which allow you to identify the composition of the material. Here's a diagram showing what I just described, an X-ray source bombarding a specimen. X-rays are being fluoresced by the specimen, and those X-rays are counted and their energies are measured by a spectrometer. Depending on which electron in the specimen atoms is filling which vacated orbital, you can get different fluoresced X-ray energies. And those fluoresced X-ray energies are proportional to the atomic number squared. That's the number of protons in the atoms that make up the specimen. So that's how you're getting the elemental composition information from the energy of the fluoresced X-rays. Here's an example of what X-ray fluorescence results look like. The x-axis is in kiloelectron volts, that's the energy of the fluoresced X-ray, and the y-axis is the count of how many of those X-rays were observed. In this case, I've put the y-axis in the square root of count to help us look at some of these small features. These tungsten sheets were 99% plus tungsten, so most of the peaks we're observing are from the tungsten fluorescence. We have a tungsten M line here from an N shell electron filling an M shell vacancy, and a series of L fluorescence lines from M shell electrons filling various L shell vacancies. The most interesting thing on this spectrum is what are all these other peaks, and why do they vary so much between the old vendor and the new vendor material? For instance, this peak here, at like 4.5 keV, we would have the K-alpha emission line for titanium, but that's not quite where that peak is. And at 5.4 keV, we would have the K-alpha emission line for chromium, and again, that's not quite where that peak is. So these peaks don't really make sense for any potential elemental contamination that could have made its way into these tungsten alloys. But this data is repeatable, and there's a definite difference between the two vendors. So we'll have to think a little bit harder to understand what this potentially means. One of the sampling artifacts you learn about when doing XRF analysis is X-ray diffraction. X-ray diffraction occurs when you're analyzing crystalline materials, and certain frequencies of X-rays are reflected back from the surface in a way that interferes constructively, causing you to receive a peak at a particular energy. This is similar to the effect that occurs when you have a thin film of oil on water, and at different angles, different frequencies of light interfere constructively, generating a rainbow effect. Typically, when you're doing X-ray diffraction analysis on an X-ray diffraction instrument, you'd be using monochromatic X-rays, X-rays of a single wavelength, and you'd be adjusting this angle theta here to measure the crystal structure of the specimen under test. On an XRF, we're doing things a little bit differently. We have a fixed angle between the X-ray source and the spectrometer and the specimen, and instead of shooting monochromatic X-rays at the specimen, we're shooting polychromatic X-rays. Because of this polychromatic X-ray source, we'll typically have some diffracted X-rays coming through, even though we have this fixed angle theta. Now, typically, when you're doing XRF analysis, you'd want to ignore these diffracted X-ray peaks. But because we know that tungsten has a body-centered cubic crystal structure with a lattice constant, that's the spacing, of 3.16 angstroms, or 0.316 nanometers, we can use that information and the diffracted X-ray peaks and their intensities to tell us things about how the crystals are oriented in the specimen surfaces. We use Miller indices to describe the various crystallographic planes in a specimen that could be generating X-ray diffraction peaks. I'm not going to get into too much detail here, but it's a three-dimensional coordinate system, and the planes described by these Miller indices will be orthogonal to the vector created by these three units here. Using the Miller indices, we can apply this equation to calculate the interplanar spacing. We can then use Bragg's law to calculate the wavelength of X-rays that would be diffracted into our detector if these crystallographic planes were parallel to the specimen surface. In our case, the spectrometer angle here is 67.5 degrees. We can then apply Planck's constant to convert these X-ray wavelengths into the corresponding X-ray energy recorded by our spectrometer. If we compare those calculated X-ray diffraction peaks for the various crystal grain alignments relative to the specimen surface with the collected X-ray diffraction and X-ray fluorescence spectra, we can see that the old vendor has an increased signal from the 200 crystal grain alignment. In other words, when the faces of the cubic structure are aligned parallel to the specimen surface. Meanwhile, the new vendor shows a more random crystal grain alignment. The more random alignment in the new vendor suggests that maybe it was rolled at a hotter temperature or rolled in a different way or annealed after rolling, all of which would explain why it was a little bit softer in our Vickers hardness measurements and why the engineers have complained that it is a little mushier and gums up the tooling when they're machining. I just find this to be really fun, to use instruments in a strange way, and here we're using something that would normally be a sampling artifact that you don't want in your data to piece out interesting information about the specimen. To me, it's interesting in the same way that all those laser diffraction and interference experiments we did in physics were good fun. I mean, sometimes it's nice to have validation that physics works. The next step was to take a look at the microstructure of the specimen surface and see how that compared with the X-ray diffraction effects we saw when we were doing our XRF analysis. Looking at the microstructure of the old vendor, we can see that indeed there are some very cubic shaped looking crystal grains, and they are aligned with their faces parallel to the surface of the sheet and their diagonals in line with the direction in which the sheet was rolled. In the new vendor, meanwhile, we don't see the same type of structure. Here's that same comparison, just at a little bit higher magnification, and yes, we can see that there are indeed some cubic-shaped crystal grains, their faces parallel to the specimen surface, diagonals aligned with the rolling direction. So this is really cool. This is why we saw that 200 X-ray diffraction peak in our XRF analysis. It's from these type of structures diffracting the X-rays back at the detector. It's always nice to go back and review the literature and confirm that what you're seeing is consistent with what's observed in literature. In this case, the earliest publication I could find was from 1936 from Wilhelm Bergers. He was looking at thinly unidirectional rolled tungsten sheets and saw the same type of behavior. Cubic-shaped crystal grains aligned with their diagonals in the rolling direction. He did a crystallographic analysis similar to our X-ray diffraction, but this was electron diffraction done in a TEM. He observed the same effect, that these crystal structures were aligned with their 200 face of the cubic structure parallel with the specimen surface. Wilhelm Burgers and his brother Johannes Burgers were pioneers of electron and X-ray diffraction. Wilhelm Burgers coined himself the uncle of the Burgers vector, which is a vector first described by his brother that indicates the magnitude and direction of the dislocation in a lattice structure. The other complaint that the process engineers had was that the old vendor material, actually, when they were trying to cut it parallel to the rolling direction or perpendicular to the rolling direction, which were most of the cuts they were trying to make, they were having a tough time with small debris particles flaking off, getting an uneven cut surface and bad finish. And I hope you can imagine looking at these structures that are aligned 45 degrees to the rolling direction, why that might be the case. And they actually changed everything and so that they were aligning their cuts at a 45-degree angle, and at that point things machined much easier. Tungsten metallurgy has seen a renewed interest in the past decade due to its favorable properties for nuclear fusion reactors. It has a very high melting point, it has low coefficient of thermal expansion, and it has good thermal conductivity. All great things for a nuclear reactor that's running at very high temperatures. It's also resistant to sputtering when impacted by plasma. A review of the literature showed several electron backscatter diffraction papers that similarly examined unidirectional, cross-directional rolled tungsten, clock-rolled tungsten. That's where you change the angle slightly each time you put it through the roller. And interestingly, each rolling type has different effects on the preferred orientation of the crystal grains. But for unidirectionally rolled tungsten, they saw the same effect, where the 200 cubic faces were aligned parallel to the specimen surface. Thanks for listening. I hope you learned a little bit about a few different analytical techniques, and I hope you enjoyed this strange case where I use spectroscopy to analyze the crystallography of a specimen and explain why it was machining differently in our processes.